Today we're going to be continuing on the linear regression stuff that we talked about last time. So what happened last time was we talked about linear regression. We derived in one dimension this closed form expression for W, which is our parameter or weight in linear regression. We talked about the intercept last time and how you can just create another feature, and that serves the same purpose as the intercept. And today we're going to generalize everything to d dimensions, and this will probably be the most math-heavy or algebra-heavy lecture in the course, as far as I can remember. So we talked last time as well about, well, we want to minimize something. Let's set the derivative to 0, and then we'll find these critical points of our function. So when we're in d dimensions, this derivative is now a gradient vector. And so we're going to set that to be 0 and solve. And so, right. Those are partial derivatives. Those are partial derivatives that are missing the line for some reason. Sorry about that. They also sort of look like a 2, so just try to make sure you don't confuse them with a 2. So this is a vector of partial derivatives of the loss function f with respect to our d parameters. Remember, we have one of these weight parameters per feature, so if we have d features, then we have d parameters. And in 2 dimensions, if we were to draw this, the loss function might look like that. And the gradient equals 0 is going to look like a situation where the tangent plane is flat, which is exactly what we want for a minimum of the function. Okay. So we will go through this in more detail in a minute, but we're going to compute this gradient vector for the least squares loss. And I've alluded to this quite a bit at the end of last class, that where we're leading to today is that we're going to solve this thing by solving a system of equations. We're going to get some big matrix equation at the end. Just to check on the microphone, since it was fixed recently, are people in the back able to hear? Okay. Okay, and we're also going to talk about this issue of, well, what if the gradient equals 0 at more than one place? In other words, what if the solution is not unique? So we talked about convexity earlier as well, and this idea that if the loss function is convex, then any of these places where the gradient or derivative is 0 would be a minimizer of our function, and that's the case as well for least squares. And the proof of this is somewhere possibly later in this lecture. Okay, so let's actually compute these partial derivatives, which is the first thing we need to do. So first of all, that loss at the top, you should be very comfortable with that thing. We will be seeing a lot of it. It's the squared error for regression, or squared error for linear regression. Any questions about the loss function? I think we talked about it quite a lot last time, but it's so important that I just wanted to give you one more opportunity. Okay, so partial derivative, meaning with respect to our different variables, let's start with W1. So first thing we can do is push the derivative through the sum, since those are both linear operations. And then we can apply the chain rule. So the derivative of that stuff squared is 2 times that stuff times the derivative of what's inside. And now we need to ask ourselves, well, what's the derivative of W transpose X with respect to W1? And now we get into the fun or pain, depending on how you look at it, of taking derivatives with respect to matrix things. This still isn't so bad. We're just taking a derivative with respect to W1, which is still a scalar, and W transpose X is not so bad, but there's plenty of this on the assignment, and it's sort of a skill that we hope you'll gain experience with throughout the course. And that's why there's a bit of that on assignment 0, just to sort of warn people in advance that we're going to be doing a bunch of this, so here it is. Okay, so that derivative is not too bad. W transpose X is a sum of terms. It's two vectors taking a dot product between them. So it's a sum of my first element of W, first element of X added all up. And now when we want to take the derivative of that with respect to W1, it doesn't look so scary anymore. We get just that first coefficient and the rest zeros. Okay, so great. This was the partial derivative I had on the previous slide. And we have this for W1, and we'll have the same thing for W2. We'll have xi2, and W3 will have xi3, and so on. So that's the partial derivative. We want it to be 0. In fact, we want all the partial derivatives to be 0. And now this thing in red is what I kept saying at the end of last class, which was, well, we want it to be 0, but look at it. It involves the whole W vector, not just W1. So if we wanted the thing to be 0, we can't just set W1 to the right thing without knowing what all the W's are. So this is what I was getting at last time, that all the W's affect all the partial derivatives, and that's why we're getting this d by d linear system in the end, instead of just d independent equations that we could just solve one by one. Any questions or comments on this? Okay. So just to reiterate some of the notation that we're going to use. Okay, I'm not going to read all of this stuff, but just to say quickly, y is a vector containing all our y values for our training set. So y is a vector of length n. xi is our ith training example. All our vectors are column vectors. And so xi is a vector of length d containing the d feature values for training example I. And then we have this big X matrix that we've been working on from the beginning of the course. And just to remind you, we should think of the rows. We always had the rows as the training examples, but if we want to be very precise, we should think of them as the xi transpose, because we're saying xi is a column vector, and if we're going to put it horizontally somewhere, then we should make that clear. Okay, a lot of stuff going on here, but really the point is this product x times w. So that's something new that we didn't talk about last time, which is we can write all of our predictions in this very compact matrix way, which is the multiplication of x times w. And there's really a lot of stuff on this slide, but the matrix multiplication of x times w is take each row of x, dot product it with w, that gives you a value. So the first element is going to be the first training example times w, second training example times w, and so on and so forth. And that's exactly what our predictions are, the training example dot producted with w. So the point here is we can compactly write y hat, which is our vector of length n containing all our predictions, as just x times w. So another thing we want to define for the purposes of today's lecture is the residual vector r, which is the difference between the prediction and the true value for each training example. So we'll have these r sub I, which is the residual for each training example. And we can have this vector r containing all of those. And we can now write things very compactly. So x w minus y gives us our error, or residual, for all the training examples, just written in that very compact notation. And in fact, the loss can now also be written very compactly. This is our loss over here in the black. It's the sum over all examples of our prediction minus the actual thing squared. We now have a new name for that, which is r squared. And so that's actually the norm squared of the r vector. Okay, so last couple slides were just notation to finally get to this thing in red. I guess sometimes we put a 1/2 there. We talked last time about how it doesn't matter that much, but we can compress the loss into just this term in red here and write it very concisely as this norm of xw minus y. Okay. We're about to get to the main part, but we're doing the setup here, getting all the notation in order before we start. So this is a whole bunch of linear algebra identities, which I would assume you guys already know from your linear algebra background. But there are more notes on the course website about this stuff. And really, the punchline here is that as you're doing stuff, and on assignment 3, you're going to be getting your hands dirty with a lot of these manipulations. Just try to check that your dimensions make sense. If you're multiplying an n by n matrix with a d by d matrix, you probably did something wrong. And it goes back to this issue I mentioned before about thinking about sizes and types, and just trying to have that awareness of the types of things, because when we just write the letter x, doesn't say it right on the piece of paper what the size of it is, but if you're not constantly thinking about it, it's easy to make mistakes. So you kind of want to turn yourself into a little compiler and give yourself these compiler errors before you write a whole page worth of stuff. Okay. Here we go. So we want to minimize this thing. In particular, we want to find the w that minimizes it, or we want to find the minimizer. So we can write our loss like this. In general, the norm squared of any vector is just that vector dot producted with itself. So that's all we're doing here. And then we can distribute in the transpose using the identity from the previous slide. So distribute in the transpose. Distribute in the transpose even more. And now we can factor this thing, or distribute out the first parentheses, unfactor. And then we can start multiplying stuff out. I did warn you there was going to be a lot of algebra in this slide, but we're going to get to a very important result at the end. So hang in there if you can. Okay. Let's be a little bit careful with this step. I guess there's maybe a step in between these two that is kind of missing. So we're distributing in the 1/2. But the key here is that we have these two middle terms on the second last line, W transpose X transpose Y and Y transpose X W. Those are both just a number. So we've been talking about dimensions, right? We have a matrix being multiplied on the left and right by two vectors. So that thing's just a number. If something's just a number, you can transpose it, and it's the same thing. It's still just a number, right? 5 and 5 transpose are the same thing. So actually, those two terms in the middle there are really the same term, and that's why we can combine them. We get two of them, then we multiply by the 1/2 and end up with one of them. And we could check our dimensions here to make sure everything's okay. So for the first term, for example, W is D by 1. So maybe I'll just do one of them on the board. So W is D by 1, which means W transpose is 1 by D. X is N by D, so X transpose is D by N. X is N by D. W is D by 1. So when we multiply the whole mess of things together, we get something that's just a number or a 1 by 1. And we can play the same game with the other two terms, just to make sure we haven't done anything crazy, right? Because the whole thing is just a loss function, which you can see from the very beginning is just a number, so hopefully it should still be a number. Okay, we're about to get to the good part, but any questions about this? We're just rewriting the loss function in a certain useful way. Okay, a lot of stuff here. The top line of this slide is just the bottom line of the previous slide. So the loss, which we can write as a sum, or we can write as a norm, or we can write as this matrix thing that we finished off with on the previous slide. Let's start to look at this thing. So we shouldn't lose sight of the fact that we're thinking of this function as a function of W. We're thinking this loss function is a measure of how badly we're fitting the data, and all we get to do is change W. We don't get to change the data, right? So we're trying to think about how does this vary with W. We're trying to pick W. We want to set the derivative with respect to W equals 0. So what is this thing when we think of it as a function of W? It's a quadratic function. So we're used to maybe one dimensions where a quadratic function is, I don't know, ax squared plus bx plus c or something like that. This is the matrix form of that, right? The general form of a quadratic in d dimensions is 1/2 x or w, we call it w transpose some matrix w plus w transpose some vector plus a constant vector, which is exactly what we have. Okay, so fine. Now we're going to compute the gradient of this thing. And if I wanted to compute the derivative of just a one-dimensional quadratic, that's what's going on here in the lower left. If everything was one-dimensional, I just had little a, little b, and little c, then the derivative of a quadratic function is just a linear function. So we can sort of expect the same thing to happen, but in more dimensions. So we're kind of imagining maybe we'll get some kind of linear function out of this. And by the way, you shouldn't be shocked that after all this rewriting, we got something that's a quadratic, because even if you look at the very original formulation there in the upper left, if you think about some particular element of W, we're doing stuff to it and then squaring it. So if we ended up that the thing was a cubic, I'd be kind of worried. Okay, so to generalize our rules of taking derivatives to matrix situations, the derivative or gradient of a constant is still 0, like you would expect. It doesn't involve W. It doesn't change as you change W. The derivative of a linear function is just that constant, just like you would expect. And the derivative of the quadratic is just a linear function. And this last piece holds true if A is symmetric. And if you look at our A matrix from up there, it's X transpose X, which is symmetric by definition. In other words, if you transpose it, you just get X transpose X back again. Okay, so here's the punchline of all that effort. Applying those definitions on the previous slide, we get to this thing on the bottom. So we have that quadratic on the top. That term becomes linear, X transpose X times W. The linear term becomes the constant vector, and the constant term goes away. So let's refresh our memories of why we're doing all this, by the way. We're trying to take the gradient of this loss so that we can set it to 0. When we're setting it to 0, we said or sort of implied that it's convex. And if we just set the thing to 0 and find a W that makes that true, then we have found the best possible linear regression for this data set, where best possible is defined by the sum of squared errors. And we're actually 90% done now, because we have that gradient, and that looks like a typo. We have the gradient with a small mistake, so this looks like should be a minus X transpose Y. So we have the minus up there, and so this needs to be a minus down here. Sorry about that. And so what we're going to do is set this thing to 0 and then solve for W. And so this sanity check thing in red is saying, well, what is the gradient? The gradient is a vector of length d, so hopefully those two pieces are also vectors of length d. And again, we can check that they are. Okay, the typo's fixed on this slide. So this is basically what I was promising you guys on Friday, which is we were going to write this thing down as a linear system. Again, just in one dimension, we could just write W equals whatever. And it was the one-dimensional version of what we have here. But in d dimensions, we have to actually perform this linear algebra operation to get W. So in a sense, we're done in that we can't really go any further than this. If you give me x and you give me y, I can call some standard piece of code that solves the linear system and gives me W, as long as everything's sort of OK with the matrix, which we'll talk about in a minute. So again, this is kind of cool. I was trying to convey last time how amazing it was that we could just plug something in and get the best possible regression without having to really, I don't know, work that hard in some sense. And it's the same thing here. And it is, again, somewhat amazing here that you give me any data set, features, examples, targets, this particular loss function, which is the squared error, and I just throw it into some solve function from whatever language. That's the one in Python. And then I just immediately get out the best possible regression coefficients. Any thoughts on this? What's your name?
Ari.
Ari?
Yeah. In what sense is this machine learning? Like, there's no learning going on.
I like that question. I like that question. The question is, in what sense is this machine learning? Okay, so machine learning, there is quite a blurred line between a bunch of different fields, including data mining, including statistics, machine learning. So the learning here is that we are trying to do something. We have a task, which is given some features. We want to predict some quantity of interest. And we're not going about, as we talked about in the beginning of the course, trying to write a program that says, do such and such with these features, maybe a bunch of if statements or whatever, and then predict that. But we're actually saying, let's automatically write that program. I mean, in a restricted sense, that we're restricting ourselves to programs where we take a vector W and dot product it with X. So we're actually only learning from a very confined set of possible programs. But once we restrict ourselves to that, we are learning it automatically from the data. And it so happens that the learning is actually not that hard in this particular case because we only have to solve a linear system to do it. But we're still deciding what to do in the future by just getting a bunch of data and trying to extract something out of it. And yes, the lines are definitely blurred. And there's all these words, as I sometimes say, there's learning and fitting and training, and they're all kind of the same thing. Question in the back, what's your name?
There's just a typo in the slides, I think, where it says numpy dot, it's supposed to say numpy dot lit.
Yeah, yes, thanks. I can fix that one right now, because it is not handwritten. Thanks. Okay, and we're not going to talk in this course in details about how do you solve linear systems. As you may know from your linear algebra class, there are ways of doing this. There are very optimized ways of doing this. And we're just going to call some standard library that does it much better than we would be able to do if we tried to implement it ourselves. Ali.
Is there any way we can get an idea of whether linear regression would be a good model for our data?
Is there any way we can get an idea of whether linear regression would be a good model for our data? So yes, and we will be talking about that. I guess a preliminary answer, and I think we may have talked about it last time too. A preliminary answer would be to look at the loss or some normalized version of the loss. And if it was, the loss is basically the training error, or what we called the training error. So we can use the same strategies as well from the first part of the course, which was validation or cross-validation. Even if our loss is 0, maybe it's not good, maybe we hold out some data, try this kind of regression, that kind of regression. So those strategies apply. Okay, incorrect solutions to the least squares problem. So in other words, don't take this too far. So if you see, these things, by the way, they're called the normal equations. Equations plural because it's a system of equations, even though there's only one equal sign. So we don't want to do something like this thing at the bottom, which is what we did on Friday. W equals this thing divided by that thing. That is okay when this thing and that thing are scalars, but it's not okay when they're vectors and matrices. And we don't want to do things like switch the order of the multiplications because matrix multiplication is not commutative. And we can maybe do this thing in green, which is, right, W equals X transpose X inverse times X transpose Y. And we still need a few more lectures, and then we'll talk more about how to make that thing invertible. So at the moment, we're going to say we're not sure yet. Okay, so why can't we just declare victory on regression and say we're done? We can do regression. So one concern is, and we'll talk plenty more about this, is this issue of uniqueness. So we might have a bunch of different solutions to this optimization problem, and we might think as humans that some of them are preferable to others, but so far mathematically we haven't specified any preference between them, and so one of them is just going to come out of our linear system solver, and we may or may not be happy with the outcome. Another question is outliers. So how do I want to say this? I would call issue number 1 an optimization issue. Sort of. Well, the solution is not unique. We don't know which one our optimizer is going to return to us. And if we want to deal with that, we may need to fiddle around with our model or with our loss function. So this outlier issue is an issue of the loss function. So our loss function is the sum of squared errors. And if we have a particular point that, say, has a y value that's really extreme, then the error is going to be whatever that difference is squared, which is going to be an enormous penalty. And so the whole line may shift substantially just to accommodate one really crazy outlier. On Wednesday and in the assignment, we'll talk quite a lot about methods that are robust outliers, but I just want to say now, even though I'm sure I'll say it again on Wednesday, don't get the wrong impression that outliers can only occur in y. You can have outliers in x or in y. And we're going to talk mostly in this course about how to be robust to outliers in y, and be aware that we won't do justice to the issue of outliers in x all that much in this course. Okay. I guess this slide is sort of foreshadowing future lectures in the next couple of weeks, because really what the next couple of weeks is going to be is dealing with these issues one by one, sort of lecture by lecture. So what this bullet point is really saying is that we will have a lecture on feature selection, which is useful because if you have features that are not actually predictive in any way or just noise or garbage or whatever, then you can actually fit to those features, or you could say overfit to those features, and that's bad. So we'll need to address that. Decision trees, by the way, didn't necessarily use all the features because they just split on whatever they wanted to split on. But the other stuff we talked about, like KNN, for example, did use all the features. Ali?
Can you set the weight value for that feature to 0?
Couldn't you just set the weight value for that feature to 0? So we'll talk about that in the lecture on feature selection. I mean, the question is, how do you decide which feature you don't want? If I know I don't want it, I can just pull that column out of X. But we need to automatically discover which features we want and don't want.
I guess my question was, because if the regression model gets us like the best possible weight vector, you would think that would figure out to make that column 0.
Yeah, if the regression is giving us the best possible weight vector, it should figure out to set that weight to 0. Sort of. So it's true. This is one of those things that if you had infinite amounts of data, you would be able to see through all of this. But if you have finite amounts of data, then you could overfit to the fact that you might see a pattern that isn't really there. So that's one issue. There's another issue, which we'll talk about in the feature selection lecture. OK. X transpose X. So that is a big matrix. That's another concern we might have. Can we even store this thing? And we'll talk about that as well. It might predict outside the range. Interpolation is always a lot easier than extrapolation. So since this model is linear, if you try to predict for something super far away from anything you've seen, the prediction will be super far away from any y value you've seen, and that might be good or might be bad depending on whether linear is actually a good model. And this is probably the biggest one, right? What if the relationship is not linear? Just like when we did k-means, what if your clusters aren't convex? Then no matter how many iterations of k-means you do, doesn't matter, right? So we will definitely be talking about this on Friday. Okay.
I have a question.
Yeah, Mohammed.
If we have enough data, can big data some sort of approximated into linear model?
I sort of understood the question, but not enough to answer it, so I'll leave it for now. Okay, Connor.
Sorry, I'm still real confused about the data storage. So X transpose X is oftentimes bigger than just X.
Yeah, Connor asked a good question. So is X transpose X actually going to be bigger than just X? So the more intuitive case is n larger than d, and certainly whenever we draw a picture, d was 2 or 1, and we certainly had more than 2 or 1 points. But we also want to consider the case of d larger than n, and we will get to that as well. It's the less intuitive and more problematic case. Okay, cost, right. So we got to form this matrix. It's a d by d matrix. Each element comes from a dot product of 2 vectors of length n. So we have nd squared cost to actually form this matrix. Then we need to solve the linear system, which takes the same amount of time as inverting the matrix, roughly, which is d cubed. And so overall, the cost is nd squared plus d cubed. And again, coming back to Connor's question, if n is bigger than d, then we would expect the first of those terms to dominate, but maybe that's not always the case. And yeah, just a little note at the bottom that it's more standard to write O of stuff and a bit strange to write O of something plus O of something else, at least to me. Okay, so this is important. So here's this sort of painful case for linear regression in terms of the solution not being unique. So imagine I have two columns that are exactly identical, which is to say I have two collinear features. Let's try to think about what that means. It means that, so I have some sum of things. Sorry, this marker is so bad. Hold on. Okay. Our prediction is the sum of terms, the w's times the x's. And imagine the column 2 and 3 of x are identical, meaning xi2 and xi3 are the same no matter which I am looking at, no matter which training example I'm looking at. Then consider these two cases. w2 is 0, w3 is 4, or w2 is 4, and w3 is 0. Those two cases will be identical in terms of the loss, because these two x values are always the same. So either I have 4 of that thing plus 0 of that thing, or 0 of that thing plus 4 of that thing. It makes no difference. Which means if the predictions are going to be the same in these two cases, it means the loss will be the same, because the loss is just a function of the predictions. So it means these two situations are going to have the same loss, which means you have this subspace of the W space that contains a bunch of solutions. And in fact, you might be thinking W2 equals 2 and W3 equals 2. That's also going to be equivalent, because I could have 0 of something and 4 of the same thing, or 2 of something and 2 of the same thing. It's still 4 of that thing if they're the same. So actually, if this is optimal, any solution with W2 plus W3 equals 4 is going to be optimal. So you have this line of solutions living inside of your space. And maybe all the other W's get specified to some value and you minimize. So this gives us the solution not being unique. And you might wonder, this also means that I could set W2 to 4 million and 4, and W3 to negative 4 million, or W2 to 1 billion and 4, and W3 to negative 1 billion. It still satisfies that situation. And that kind of sounds like overfitting, because maybe those two things were the same or close to the same in your training set, but maybe when I'm making a prediction, one of them is 0 and the other one is not 0, and do I really want to be multiplying that thing by 1 billion for no reason and getting predictions of magnitude 1 billion, which is maybe totally ludicrous for the application I'm working on. So it's not just a nuisance that the solution's not unique. Yeah, it'd be great if it was unique. If I ran the code and you ran the code, we'd all get the same solution. Great, it's unique. That's nice, but it's also that we're exposing ourselves to completely crazy values of W, and that's a little bit worrying. So that's something we're going to talk about. We're going to solve that problem next week, but I want you to understand it today. Liam? All right.
Is this actually an issue that you encounter?
Is this actually an issue that you encounter, that you have two identical features? So you could, I mean, first of all, that could just happen not because you collected data and that happened, but because there's some issue in your data table and you want your results to make sense nonetheless. But we will talk about that later as well, and also talk about very similar features. Okay. Great. We talked about convexity only a little bit 2 classes ago in the optimization introduction class, and I referred you some notes about convexity which are posted on the website, which are basically rules for figuring out if something is convex. And this slide is saying you can apply those rules to show that this loss function is convex because norms are convex and the inner thing is a linear function of w, and if you have some convex function of a linear function, then the output is also convex. So you can see those notes for more details on this, but what we really care about is the result. And so this plays back into this uniqueness thing that we were just talking about. So on the one hand, we shouldn't be worried because we're not going to have a local minimum, for example, that's not nearly as good as some other global minimum. This is telling us that we may have a bunch of minima, but they're all equally good, which seems like good news. But then there's the associated bad news of the previous slide, which is that while all the solutions are equally good in terms of training error, which is what this loss is, some of them make no sense. Or it can be arbitrarily crazy in terms of the predictions, and so we really need to work on that next week. Cool. Okay. Today, we talked about the normal equations, which are this thing at the top, except it'd be nice if that T was capitalized. Let's do that. Okay. We talked about how the solution might not be unique, and collinearity, meaning 2 features are the same. We built this intuition about how we get this space of W's that are equally good. And we talked a little bit about convexity. So that's it for today, and see you